Welcome to the deep dive. Today we're jumping into a really big topic, sustainable design and green engineering. It touches, well, pretty much everything.
It really does. We're digging into some key ideas from sustainable design, the science of sustainability and green engineering by Valero and Brichier.
Yeah, and the goal isn't just to skim the surface. We want to give you a shortcut to understanding the core science, the history behind it all, and the ethical side, which is huge.
Exactly. We'll unpack how design thinking has shifted, the science you absolutely need to know, some really cool new models inspired by nature itself, and yeah, the critical stuff around ethics and environmental justice.
Okay, so let's start with a bit of history. The book mentions this idea of the master builder back in the Renaissance.
Right. People like Brunelleschi. They didn't just design, they knew how to build it, top to bottom. Design and technical skill, all in one person.
But then the Industrial Revolution kind of fragmented that, didn't it?
Totally. Things got specialized. Design became separate from the making, especially with parts being manufactured elsewhere.
And that led to this traditional design model the source talks about, like a straight line.
Pretty much. Conceptualize, plan, document, build. Step by step.
Okay, but what about feedback?
Well, yeah, there were feedback loops, but often they came really late,
Mm.
which meant delays, extra costs, that kind of thing.
Mm.
And a key point the book makes is that this old way of thinking often acted like resources were just endless. It sort of ignored fundamental science like thermodynamics.
Which is wild when you think about it, because almost everything we do affects the planet, right? Heating water, using electronics.
Exactly. And it's not magic, it's science. You can explain the impacts.
So that scientific reality must have pushed things forward towards thinking differently about pollution.
Definitely. The early days were all about end-of-pipe solutions.
Right. Build the factory, then figure out how to scrub the smoke and treat the wastewater afterwards, cleaning up the mess.
hmm But then you had the environmental movement picking up steam in the 60s. Ideas like spaceship Earth, this notion that we're on a finite planet.
That must have been a big shift in perspective.
Huge. And it connected with other social movements. The book even mentions how culture, like music, they cite Quicksilver Messenger Service, reflected these growing worries about, poisoned air and water.
And then came the really stark wake-up calls, the disasters.
Yeah, the source mentions Seveso, Love Canal. These raised alarms about industrial pollution even before some of the ones we might think of first.
Like 3 Mile Island, Bhopal.
Chernobyl, the Prestige oil spill.
Uh,
Those absolutely focused public attention and pushed for policy changes. They really brought home the risks.
so all this pressure, public, regulatory, even economic, started shifting the focus from just cleanup to prevention.
Exactly. Companies started seeing that actually preventing pollution at the source, being more efficient, eliminating waste before it happens. It saves time, it saves money, it saves resources.
The whole pollution prevention pays idea.
That's the one. It requires thinking about the entire system, the whole product stream, not just the output pipe.
Which I guess brings us right back to the science. You need to understand how things actually work.
Absolutely. The book hammers this home. Sustainable design has to be built on sound science. Understanding the rules lets you work with the environment, not against it.
Okay, so let's break down some key scientific areas the book highlights. Thermodynamics first.
Yeah, the big one. Conservation of energy. You can't create it, you can't destroy it, you just change its form.
And the implication for design. Old ways ignored this, treated energy as limitless.
Right. But if you know energy is conserved, but you lose useful energy with every conversion, well, then efficiency becomes paramount. Sustainable design has to minimize those wasteful conversions.
Makes sense. What about how things move, fluids?
Fluid dynamics, yeah.
Mhm.
How air and water flow, things like viscosity. This isn't just textbook physics, it's super practical.
So for, say, a building.
Well, if you understand airflow, like how warm air rises the stack effect, or how air speeds up through narrow spaces, the Venturi effect, you can design ventilation systems that need less mechanical power, maybe none in some cases.
Passive systems.
Exactly. And using thermal inertia, how materials store and release heat slowly, that helps regulate temperature without constantly running the heating or AC.
Okay, what else? Energy itself.
Just reinforcing that it's about the potential to do work. Understanding conservation, the work-energy relationship W equals delta E, that's fundamental for tracking energy use in any design.
Then there's electromagnetic radiation, EMR, light, heat.
Right. And the key difference the book notes is between ionizing radiation, like X-rays, which has enough energy to knock electrons off atoms, and non-ionizing, like visible light or radio waves.
How does EMR play into sustainable design?
Well, light pollution is one example. Badly designed outdoor lighting messes up ecosystems, particularly for nocturnal animals.
Ah, all right.
And understanding how surfaces interact with radiation is key. Things like albedo, how much light gets reflected, and emissivity, how much heat gets radiated out.
So like a white roof reflecting sunlight.
Precisely. High albedo reduces heat gain, cutting cooling costs. The book even has data tables showing these properties for different materials.
Chemistry must be huge too. Redox reaction.
Oxidation reduction.
Yeah.
Yeah, fundamental. They power life metabolism, but also cause pollution, like smog formation.
So understanding them helps us control them.
Exactly. We can use oxidation to treat nasty stuff like cyanide, or reduction to deal with heavy metals. The source even mentions how certain bacteria produce hydrogen sulfide gas in anaerobic conditions, think sewer gas, through redox.
And this ties into how chemicals move around, nutrient cycles.
Yeah, like nitrogen and sulfur.
Mm-hmm.
These elements cycle naturally through air, water, soil. They're essential. But human activity can overload these cycles. Too much fertilizer, for instance, leads to excess nitrates in water. Something good becomes a pollutant when it's out of balance or in the wrong place. You get that system-wide view.
Got it. And organic compounds, carbon-based stuff.
Small changes in structure can make a massive difference. The book uses examples like ethane versus trichloroethane. One's a simple gas, the other's a solvent, potentially toxic. Adding a chlorine atom changes everything. Solubility, toxicity, how likely it is to build up in living things. Benzene versus toluene is another example. Understanding structure helps choose safer materials.
So important for avoiding unintended consequences. Lastly, environmental media. Air, water, soil.
Thinking of them as compartments, chemicals move between them, they react, they partition, meaning they prefer to be in one medium over another. How long does something stay in the air versus the water? What happens to it there? That's crucial for predicting environmental fate.
Okay, so with all that science as a base, designers are starting to move beyond that old linear model.
Yeah, definitely. There are some really interesting new approaches emerging. Biomimicry is a big one.
Janine Benyus's idea, right? Learning from nature, not just taking from it.
Exactly. Nature's had billions of years of R&D. The book gives great examples: solar cells based on leaves trying to replicate spider silk, ceramics inspired by mother of pearl. Even thinking about whole systems, like creating closed-loop economies modeled on ecosystems where waste equals food. It's very gestalt. The whole is more than the sum of its parts.
Cool.
Yeah.
What else? Synthivation, regenerative model.
Yeah, those emphasize integration, synergy. Instead of linear steps and late feedback, it's more of a spiral.
A spiral, how does that work?
You're continuously integrating different aspects and refining the design from the very beginning. You can actually make adding sustainable features more cost-effective because they're baked in, not bolted on later.
And tech helps here.
Big time. Collaboration software, building information, modeling BIM. These tools let engineers, architects, cost estimators, even operations people all work together much earlier in the process. BIM can integrate time, cost, sustainability factors right into the 3D model.
That sounds like concurrent engineering too, getting everyone in the room from the start.
Very related. Breaking down those sequential silos, getting all the perspectives working together simultaneously.
Makes sense. And then there's appropriate technology. What's the focus there?
It's about context. Designing solutions that fit a specific place. It's geography, culture, economy.
Especially in the developing world.
Often, yes. The idea is to use local labor, local materials if possible, so the benefits stay local. Improve quality of life in a way that's sustainable for that community. The book mentions solar panels in a rural Ugandan village as an example installed using local expertise.
And we see these ideas put into practice in things like green buildings, right? LED certification and so on.
Exactly. LD provides a framework, encourages practice that minimize negative impacts. The source uses the Home Depot Smart Home at Duke University as a case study.
What did they do there?
Lots of things. Solar panels offsetting a good chunk of their energy use, a big rainwater harvesting tank, diverting a majority of their construction waste away from landfill.
And students got involved too.
Yeah, applying these principles. One project looked at campus energy, comparing coal alternatives based not just on environment, but cost and availability. Green steam, they called it. Practice. Another used harvested rainwater, first to cool the solar panels, making them more efficient, and then used that slightly warmed water for radiant floor heating. A really smart closed loop.
That is smart. Saves potable water too.
Thousands of gallons. And another project, AgriMix, developed a biodegradable material from plant waste for things like, toilet paper rolls. Simple stuff, but it adds up.
And they looked beyond just the tech.
Right. The source mentions student work on the human side, social justice, policy incentives, education, even a water purification project in Africa linked to local industry. It's holistic.
That brings up another point: what happens after a product or building is done? End of life.
Design for disassembly, or DFD. Thinking ahead, how can this thing be taken apart easily? Can the materials be reused or recycled effectively?
The book has that anecdote about the disposable razor.
Yeah, sitting in a landfill basically forever. That's what happens when end of life isn't part of the initial design thinking.
So DFD encourages designing things that can be adapted or easily broken down, unlike, say, a cheap strip mall.
Yeah. Exactly. Designing for longevity and adaptability, long life loose fit, versus designing for disposal. It's all tied into life cycle analysis, LCA.
Assessing the total impact.
From extracting raw materials through manufacturing, use, and finally disposal or recycling. Cradle to grave, or even cradle to cradle. LCA helps you see the hidden impacts.
Like the solvent example.
Right, switching from a petroleum solvent to a water-based one. The LCA showed the water-based option was way better overall, preventing hazardous waste right at the source. It's not always obvious without that full analysis.
Okay, this really flows into the ethics of it all, doesn't it? The book seems to say sustainability and ethics are inseparable.
Absolutely. Ethics is about what we ought to do. And sustainable design forces us to think about our obligations to others, people far away, future generations. The source even calls green design a virtuous endeavor, linking it back to Aristotle.
A green categorical imperative, what's that about?
It's this idea that you judge a design not just on one benefit, but on its cumulative impact over its whole life. Is the total outcome right or wrong? A design might seem efficient now, but if it creates toxic waste later or uses conflict minerals, is it truly ethical?
That's a high bar. What about risk?
Risk and reliability are framed as ethical responsibilities too. Designing things to be safe, dependable that's core to professional accountability, though safety itself is relative, involves judgment calls.
And this relates to the tragedy of the commons.
Yeah, Garrett Hardin's famous parable, each herdsman adding one more cow to the shared pasture seems rational individually, but collectively it destroys the resource.
How does that apply here?
The book uses the example of greenhouse gases and asthma inhalers. A tiny amount per inhaler seems insignificant, but multiply that by millions of users over years. The cumulative effect on the ozone layer or climate change becomes massive. Designers have to weigh the medical need against that collective environmental harm. It's a tough trade-off.
Which puts a lot of responsibility on designers.
A huge amount. The book stresses that competence has to be linked to character, ethic, arete. The ultimate client is the public. Their safety, health, welfare have to come first, above profit or other demands. That obligation is a driver for being green.
And this responsibility has to include fairness, right? Environmental justice.
Critically important. EJ recognizes that environmental burdens, pollution, hazards, risks haven't historically been shared equally. Design decisions can end up disproportionately harming certain communities.
Often poorer communities or minority communities.
That's often the case, yeah. And the source points out it's not always deliberate malice or pure profit motive. Sometimes it's public agencies making decisions based on budgets or where they expect the least political resistance, citing landfills, waste facilities, unpopular projects.
Vexation without representation, the book calls it.
A striking phrase. Assessing EJ means looking for those disparate effects. Are disease rates higher here? And also, disparate susceptibility. Are some groups, like children, inherently more vulnerable?
So you need the science, epidemiology, maybe even genetics, but also the social context.
Absolutely. The source uses specific cases, like the Warren County PCB landfill or the proposed Shintech PVC plant, as examples discussed in the text to illustrate these conflicts, the siting decisions, the community pushback, the mix of economics, politics, and potential injustice. It mentions Charles Lee's important work in formalizing EJ concerns. These aren't simple issues.
No, clearly not. The book also touches on the scientists' role in all this.
Briefly, yes. Scientists influence policy, face a dual-use problem where discoveries can be used for harm, and have that fundamental ethical duty C.P. Snow talked about. Seek the truth and tell the truth.
And it connects to broader philosophical ideas.
Yeah, it mentions different ethical frameworks, duty ethics, utilitarianism, greatest good for the greatest number, contractarianism, social agreement, just showing that philosophers have wrestled with what is right and just for centuries, and these ideas underpin how we should think about sustainability and justice today.
Wow. Okay, we have covered a lot of ground, from the history and evolution of design.
Through the essential science, energy, chemistry, environmental flows. than those innovative models like biomimicry and integrated design.
And finally, landing on these really fundamental ethical questions of responsibility, justice, and long-term impact.
Yeah, the big takeaway really seems to be that sustainable design isn't just one thing. It's integrating the science, changing the process, and embedding that ethical commitment to fairness, both now and for the future.
And knowing about this stuff isn't just academic, right? It helps you understand the world around you, the buildings, the products, the systems we all live with.
Definitely. And maybe, based on that green categorical imperative idea and thinking about long-term consequences, here's a final thought to chew on.
Okay.
How might the tiny design choices being made today, or even our own small actions, add up? What kind of cumulative effect will they have on the world, say, centuries from now, or even millennia?
That is a powerful thought, something to really reflect on. Thank you for joining us for this deep dive.